Welcome everyone to this section on generative adversarial networks, or GANs, G-A-Ns. So it's time to learn about the GAN, or generative adversarial network, and they were first reported in 2014 from Ian Goodfellow, as well as his other co-authors working in the same lab. So as you can tell, this is a really new technology, and it's a really exciting technology in the space of deep learning. GANs basically have the capability to generate new samples similar to the data they were trained on. So for example, they can create new faces after being trained on a large data set of real faces. So they will actually generate faces that mimic a real person's face. So they've been able to achieve some incredible results. Here we can see that just after a few training epochs, the network is actually able to, after being trained on images of faces, begin to generate its own faces. Now, after 5 epochs and even after 100 epochs, you can definitely tell here that these aren't real people. They're kind of distorted images. But some of the latest results from NVIDIA, and this is from basically late October 2017, so very, very recent results as far as the filming of this presentation. These are fake celebrities that a network has generated. So none of these people are actually real. The network itself generated these images, and they look very convincing. If you start looking closely, you can tell that certain things are off, but this is really incredible work from the latest results of NVIDIA. So let's go over the general idea of how GANs work. We're going to end up to create a GAN, build two networks, a generator and a discriminator. And these networks basically compete against each other. So the classic analogy for GANs is the forger versus the detective. So you have a forger trying to forge paintings and make them real enough that the detective won't notice. And you can think of the forger as the generator and the detective as the discriminator. So you have these two networks, a generator, which we have here in that little blue box, and a discriminator network in that little like pink orange box, and they're competing against each other. And basically what happens is the generator makes fake data to pass the discriminator. So the discriminator also sees real data, that is real images, so for example, real images of paintings or real images of faces, and it predicts if the data it received is real or fake. And the generator is being trained to try to fool the discriminator. It wants the output data to look as close as possible to real data. And the discriminator is trained to figure out which data is real and which data is fake. And what ends up happening is that the generator learns to make data that's indistinguishable from real data to the discriminator. So if we follow this kind of example here, starting from the top, we have some real data, and we take in some sample data from the real set, so in this case like a real painting, and we show that to the discriminator, and the discriminator tries to decide whether it's real or fake. So it's been trained on real data. Then we have latent data, so that can start off as random noise that we feed into the generator, and the generator is then trying to fool the discriminator. So it'll slowly generate pretty poor examples trying to mimic the real data, and as it gets trained off the trying to basically fool the discriminator, it gets better and better. So the latent sample is basically a random vector that the generator is using to construct its fake images. And as the generator learns through training, it can figure out how to map these random vectors to recognizable images that can fool the discriminator. And it doesn't actually have to be just images. Images are the most famous example of GANs, but you can also do things like using GANs to try to generate, for instance, audio data. So eventually, after a lot of training and usually a lot of tuning of hyperparameters, the generator will hopefully be able to generate examples that are indistinguishable from the real data. Now, coding out a GAN can actually be relatively simple. You're just essentially making two networks that we've done a lot in the past, and we're going to use the TF layers API to make that even simpler for us. So it's just a discriminator network and then a generator network. What isn't really simple is the tuning of the hyperparameters and the training time involved. So let's briefly discuss some potential problems that occur with GANs. One potential problem is the discriminator overpowering the generator. So sometimes the discriminator, remember that's the network that's trying to tell whether or not something's real or fake from the generator, it can sometimes begin to classify every single generated example as fake. So what you may want to do to fix that is have the discriminator output be unscaled instead of a sigmoid, because remember the sigmoid function returns something that's always 0 and 1, or between 0 and 1, and that may cause the discriminator to just shoot everything down to 0 and have it all be called fake or false examples. There's also another problem that's known as mode collapse, And that's where the generator discovers some sort of weakness in the discriminator. Maybe if a certain section of an image has red pixels in it, the discriminator automatically says it's real. And what ends up happening is the generator just keeps sending the same image over and over again because it basically found this little trick to fool the discriminator, some sort of weird potential weakness. And the generator is basically continually producing a similar example regardless of whatever variation you provide it in its latent sample input. So the one way you can know if that's happening is if your generator, as you check it, keeps producing the same data over and over again. One way to fix this is you can try to adjust the training rate, maybe slow it down a little bit, or you can even change the layers of the discriminator in an attempt to make the discriminator better at detecting a real sample versus a fake sample to avoid that potential weakness. Now keep in mind this technology is extremely new. It was just published in 2014 and the latest techniques are constantly being published. Like we just saw, that NVIDIA paper was just published as far as the time of this filming less than a few weeks ago. Now, realistically, if you're serious about GANs, only a GPU-powered computer is going to be able to handle the training of a GAN in a reasonable amount of time. That's not to say for simple problems, a CPU won't be able to handle it. A CPU can handle it. It's just going to take a really long time. You'll have to probably wait hours or days for a really simple problem if you're just running it on CPU. Now, with more complicated problems, such as generating those faces we just saw, really GPU is the only realistic way to do it. And even then, if you have a really strong GPU, for certain problems, it can take a really long time, like days to weeks for certain data types. So keep that in mind. This is really going to be limited by your hardware as far as what problems you can tackle. So if you're locally limited to kind of mediocre hardware, you may want to look for a service online that allows you to access higher powered GPUs. So what we're going to do now is code out the most famous example of a GAN, and that is creating a GAN that generates numbers based off the MNIST dataset. So we're going to hop straight into that in the very next lecture. Thanks, and I'll see you there.